let's take a look at our first example of the types of integrals that you'll encounter in section 7.1. So there's no new techniques of integration. It's just building on u substitution or doing some sort of algebraic manipulations before you actually do the integral. We'll get to the other techniques in 7.2, 7.3, 7.5, and then we'll come back to 7.4 after the gateway. So I had mentioned in class that the go-to method that you should try first if you have a rational function is maybe this antiderivative will be a natural log. So we would want to let u be the x squared plus 9 in the denominator, but something's going to happen. So if you look at what's going to happen here, we are going to run into an issue. And that issue is going to be not being able to cancel our x's. Right, so we make our u substitution, and we would like to be able to cancel this x and this x. Okay, but thanks to this subtraction of 2 right here, that's going to mess us up. You can't cancel things across fraction bars where you have stuff separated by addition and subtraction. So this is not going to work. Okay, so there's going to be a different trick that we can do. Okay, now since the subtraction of 2 is messing us up, well, why don't we just break apart our integral into 2 separate integrals and see if that will enable us to solve those integrals. All I did is forget my dx. All I did was break apart the fraction across the subtraction in the numerator. So remember, you're allowed to break apart fractions over addition and subtraction that's in the numerator, but not the denominator. We're basically just undoing the putting the fractions together with how you would add fractions. Okay, so just broke apart right there. Now we can look at this in 2 pieces. Okay, this integral, if we make this u substitution, right, we'd still get this du over 2x, but look what would happen. We don't have this minus 2 here, so you can kind of ignore this for a second. These would now cancel. Okay, this first integral then is a u substitution that'll net us a natural log. So all the u substitution is going to do is get us this factor of 1/2 that we're missing. I had mentioned in class that u substitution is just a tool in order to recover missing coefficients. Okay, after you do enough of these problems, you're really going to notice what sort of substitution or what factors that you're missing without actually doing it. But if you need to pause the video, actually work through the u substitution, by all means, do it. You're still going to get the same result in the end. Okay, so we'll just look at these in pieces. So this first one, this will just be 1/2 natural log of x squared plus 9. Okay, now there should be absolute value bars here, but x squared plus 9 is not negative, so they're not needed. Also, this plus c, we're not going to write because we're going to have 2 of these integrals, right? They would technically both get a plus c, and then an arbitrary constant plus an arbitrary constant. It's still just an arbitrary constant, so we're just going to ignore it. Get the antiderivative for this one, the antiderivative for this one, and then just slap the plus c on at the end. Okay, so this one's done. Bam. Now let's look at this. Let's look at this guy. So we have the integral of 2 over x squared plus 9 dx. And if you want, which we should, maybe it'll help us see what it is, let's move the 2 outside. You can think about what antiderivative this would be. It's not going to be another log, right? Because if I have u be x squared plus 9, I don't have an x to cancel like we would have right here. Okay, but we had talked about what the antiderivative of something that looks like this is. If u is a differentiable function of x, and this is what? 1 over a arctangent of u over a plus c. Okay, where my a here is 3, and my u is just x, because here's my du, or my du would be this. So this is just going to be 2/3 arctangent of x over 3. And this one's done. So we're ready, right? We have this antiderivative, the first guy, minus the second one. Gives us our integral that we want. So our antiderivative is going to be 1/2 natural log of x squared plus 9 minus 2/3 arctangent of x over 3 plus our integration constant. And there we go. Okay. So as you'll discover from doing problem after problem after problem, the hard part's going to be, after we develop all these techniques of integration, identifying which technique is needed for any particular problem. So again, the go-to method I still think should be, maybe this integral is just going to be a log. And if it is, great. If it's not, try breaking up the addition and subtraction. If you have any in the numerator, break it up and investigate what each of the pieces do. If that works, great. If it doesn't, then we'll talk about some other things that you can try. So if you want, you can go ahead and just pause the video. We're going to do 2 more examples, but if you want, the first problem in the 7.1 homework is pretty similar to this. So if you want to pause the video, go hop into my math lab, do problem 1 of section 7.1 and see what you get. And then we'll continue on our little discussion here. All right, our next example also is a rational function. Okay, but the thing that's different about this one versus the one that we just looked at is the first example, this rational function was proper, meaning the degree upstairs, which is 1, was less than the degree that was downstairs, which is 2. So here, our rational function is not proper. Okay, they're both degree 1 polynomials. So if we tried to just break apart the fraction like we did before, this is one way that you could do this, okay, but I don't think it's going to be as straightforward. This guy right here, this is going to be another natural log. Okay, this not quite, right, because the derivative downstairs is 1, and I have this pesky x sitting up there. Okay, you could do it this way. I don't think it's going to be as straightforward. Okay, so what we're going to do first is we need to rewrite this rational function so it's proper. So if you remember back from algebra, which was however many semesters ago, just do long division here. Okay. So if you haven't done this in a while, it's not that hard. I always tell people I think long division of polynomials is easier than long division with numbers, just because there's a lot less arithmetic that happens. But my college algebra students tend to just still run out of the room screaming, but it is what it is. Anyway, you want this x to be an x. So what do I have to multiply this x by so that he is an x, and that is 1. Okay. Now, regardless what this is, you then distribute this into your divisor, the guy on the outside of the house here. So you're going to get x minus 8, and then subtract off that guy. So the x's go away, which is good. Then we have 4 minus a negative 8, so 4 plus 8, which is 12. Okay, now the x's can't go into here anymore. So what this tells us right here is that x plus 4 over x minus 8 can be rewritten as the quotient, your answer from the division, plus the remainder over the divisor. So 1 plus 12 over x minus 8. Okay? So that tells us here that my integral, this guy, is going to be equal to the integral of 1 plus 12 over x minus 8 dx. Okay, now we're good to go. Right, the antiderivative of a constant is just slap the x on, plus this is going to be another natural log, right? The derivative of x minus 8 is just 1, so the 12 will just come along for the ride. So 12 natural log of the absolute value, x minus 8 plus c. Now I do need the absolute value bars here versus what we had up here, because this stuff inside the natural log, this was never negative. This can definitely be negative, so yes, we need the absolute value bars here now. Okay. So again, the good way to remember long division, let's just look at one that's a little bit more complicated, I guess. Since this example was a little short. The divisor out here, the x wants to be a 4x squared, so I have to multiply by a 4x in order for x to become a 4x squared. So distribute the 4x into the x minus 5. So we'll get 4x squared minus 20x. And then subtract off the whole thing. So always remember these parentheses here because the negative has to distribute. You get 4x squared minus 4x squared. Those drop out. Negative 10x plus 20x is a positive 10x. And just like from elementary school, drop down the next guy. The x wants to be a 10x, so we need a plus 10. Distribute the 10. Again, these terms should always drop out at every step. Okay? So you get 10x minus 10x goes away. 1 minus a negative 50 is a plus 50, so you get a positive 51. So in this case, what 4x squared minus 10x plus 1 divided by x minus 5, this could be rewritten as 4x plus 10 plus 51 over x minus 5. So again, it's always the quotient, which is the answer from doing the division, plus the remainder over the divisor. Okay, so if we were asked to integrate this dx, it's the same thing as just integrating this. So this would just be a power rule here. Oops, 2x squared plus 10x. And again, this would be another natural log here. So it enables us to solve, different types of rational function integrals. The takeaway here, again, in words, if you have to integrate a rational function and it's not proper, meaning the degree upstairs is not less than the degree downstairs, try rewriting it with long division. If that works, great. If it doesn't, try something else, I guess. Okay, so we'll do one more example. Again, the next problem, so in section 7.1, so problem 2 is something similar to this. So go ahead and give that a go, see what you do, or see what you get, and then we'll do the last example that we'll talk about. All right, last example. Again, look, another rational function. So I guess because 7.1 is just rational function. Actually, it's not, but they're the ones that tend to be probably the trickiest when you're first starting out. All right, this one is going to be slightly, I don't want to say harder. It's going to be harder in respects to the algebra that you have to do in order to integrate this. But the thing that's very different, right, where are we? So the second example that we did, right, we had an improper rational function. The trick here was use long division of polynomials to rewrite your rational function and then integrate. Similarly, we had a proper rational function, but we had some addition or subtraction in the numerator and we split up the fraction. We don't have that here. So what we're going to want to do is we're going to want to complete the square on the denominator so that it will look like something that we can integrate. Okay, so the trick here is we want to complete the square. Now, I know a lot of people tend to not like completing the square, but let's just go through. So to complete the square, you want to look at b, the coefficient on x, and you want to take half of the negative 4 and square it. So we're going to have x squared minus 4x. If I take half of negative 4, that's negative 2. Negative 2 quantity squared is 4, so I'm going to add 4. But I can't just add 4 to something, so I'm going to have to subtract 4 immediately so that I only add a 0. Okay, so again, take half of b, square it, add, and then subtract that. The reason why we're doing that is that stuff factors. This will always factor as x plus or minus a number, and the plus or minus is determined by the sign on your x term. So x minus the square root of the number that we just added. Okay, like I said in class, whenever you factor anything, I think a good rule of thumb is always expand it back out, at least mentally, make sure you factored it right. There's no need to mess something up, for some silly mistake or whatever. And then just combine these two guys. So we have negative 4 plus 13 is plus 9. Okay. So this tells us then that our integral, so we have the integral of x squared minus 4x plus 13. This will be equal to the integral x minus 2 squared plus 9 dx. Now, hopefully this looks familiar. This is going to be another one of those integrals of u prime u squared plus a squared du. Where what is my u going to be here? The u is x minus 2. Here's my du. And my a is 3. So this integral then is going to be 1 over a. So 1 over 3 arctangent of u, x minus 2, over a, plus our integration constant. Okay, so there you go. Another arctangent. We could have had this set up where maybe this was a square root and you end up getting, after you complete the square, you can get a guy like this, which this is an arc sine. So arc sine of u over a plus c. So just practice doing some completing the square problems. If you want a whole lot of practice, you can easily make up your own completing the square problem. Just start with something that looks like this. Right, expand this all out and then go backwards, and then you should be able to get right back to where you started. If if it's been a while since you've done completing the square. But yeah, we'll use completing the square a little bit more, and I forget which section it is. I want to say 7.4. I think I want to say 7.4. But anyway, just practice. Problem 3 on the section 7.1 homework is similar to this. I think in the directions it actually tells you to complete the square. So not all the problems will tell you what to do, but just be aware if you see something like this, chances are, or if you just have a quadratic down here like this, chances are it's going to be a completing the square type problem that you want to do. So that's that. So make sure to get the 3 problems done for the homework before class, and the notes, they're all on Blackboard, but the notes aren't going to be regular notes for these 4 sections that we'll do. There's like a 10 problem worksheet. And so what I want you guys to do is when you come to class, show me, you worked through these problems with me, or you took some sort of notes, and, get the homework done, or the little homework assignment, the 3 problems, and then show up to class, and, I'm just going to have you guys work on those problems, because really the Gateway exam is just a mechanics exam. Can you do these problems? There's nothing overly tricky, so it comes down to practice. I will see you guys in class.